Hi, everyone. Good afternoon and good morning to all our participants today here in the second technical meeting of Communities of Practice on Air Quality in Asia Pacific with our session, Sensors Making Sense, Use of Hybrid Air Quality Monitoring Systems in Asia. This meeting is made possible by the UN Environment Program or UNEP, Asia Pacific Clean Air Partnership or APCAP, and partners such as Clean Air Asia, with support from the United States Department of State, in line with providing support to regional communities of practice on issues critical to air quality management in Asia Pacific. So I'm Everlyn Tamayo. I'm the Air Quality Specialist of Clean Air Asia, and I will be your host and moderator for today. To share a bit about my experience, I've been working on atmospheric pollution analysis and air quality management and the use of data analysis and capacity building to inform policy development towards improved air quality. In the organization, my role is to provide technical guidance in current and emerging air quality issues in the region, such as the use of hybrid air quality monitoring systems. So before we start, we'd like to remind you to please rename your username here in Zoom with your name, affiliation, and country so we can address you properly. Kindly keep your microphones in mute and feel free to turn your videos on if you are comfortable with it. Please be reminded that the meeting video and chat will be recorded. Please type in your questions or comments in the Zoom chat box and moderators will acknowledge them as time permits. We wish you that you will all have a pleasant learning experience in today's session. To officially start our meeting, we would like to thank you all for attending this event. I think we are one in the goal of wanting to learn and improve air quality monitoring systems, and this session will indeed tackle important topics in relation to hybrid monitoring, which combines non-conventional methods such as use of non-reference or low-medium cost sensors and remote sensing techniques, which we combine with conventional or our reference level instruments. So without further ado, I would like to introduce and call on our speakers who will give the opening remarks. The first speaker is Mr. Thomas Schmidt, the Director of the Regional Environment, Science, Technology, and Health Office for the East and Southeast Asia. He serves as the U.S. government's primary point of contact in the field on the Mekong-U.S. partnership and develops policies and programming suggestions for U.S. government consideration. His work focuses on a broad range of climate and environment topics, including addressing air pollution issues. I will now give the floor to Tom.
Thank you, Ever. Good afternoon, everyone joining us today for the second technical meeting of the Regional Communities of Practice of Air Quality, Sensors Making Sense, Use of Hybrid Air Quality System Monitoring Systems in Asia. I want to thank the UN Environment Program, the Asia Pacific Clean Air Partnership, and Clean Air Asia for hosting this event and inviting me to speak. As we all know, air pollution presents a severe and pervasive threat to millions of people's quality of life and health in the world. And the challenges to addressing these issues are persistent and widespread. Each year, about 7 million premature deaths worldwide are attributed to air pollution, with more than 4 million of those deaths occurring in East and Southeast Asia. And like all forms of environmental pollution, air pollution is not stopped by political boundaries. The transboundary nature of this environmental threat makes international cooperation all the more important. That is why today we have gathered decision makers, policymakers, and technical officers from national and local environmental agencies who are responsible for air quality monitoring and related activities. And we have international and regional experts from academia, international organizations, and industries focused on air quality monitoring and management to foster collaboration between the stakeholders in the region. Over the past decade, the United States has dramatically increased its international engagement on air quality issues. Yet in recent years, research has again and again found that we have greatly underestimated air pollution's human and economic costs. In the United States, we have made tremendous progress in addressing air pollution. Since passing the Clean Air Act in 1970, we have reduced air pollution by 70%, while growing the US economy by 246% over that same period, proving that environmentalism is not counter to economic growth. Even so, the US Environmental Protection Agency estimates air pollution is responsible for 135,000 deaths in the United States each year. So we know that improving air quality is possible, but it is a long, ongoing process requiring commitment and persistence. Air quality is one of the United States' top environmental priorities in East and Southeast Asia. We are working closely with countries and stakeholders across the region on this issue. A crucial part of our engagement is through the Department of State's Air Quality Program. This program strengthens and brings about action in places where it can reduce severe air pollution and its transboundary impacts. In addition, the program reinforces air quality management networks in critical regions and fosters regional leadership and cooperation. These air quality projects promote the use of the best available technologies, data transparency, and new and strengthened environmental protection policies, including high standard air quality laws, regulations, and programs in partner countries. We also work to enhance data coverage, accuracy, precision, data management, and expand awareness and understanding of air quality among practitioners, decision makers, and the public. The United States Department of State has also contributed directly to the availability of quality data through our own diplomatic missions worldwide. Over 70 US embassies and consulates, more than half of them in Asia, have installed reference-grade air quality monitors. In addition, they publish real-time data on the US Environmental Protection Agency's AirNow website, the same site we use to display US domestic air quality data. The two elements are common to most of our air quality projects. First, having publicly available quality data is crucial to making real progress. When society understands the level of pollution in the air and its effect on the health of their loved ones, they tend to push for cleaner air. Many of our programs generate quality data through hybrid air quality monitoring systems. One project implemented by RTI is creating a network of low-cost sensors in Southeast Asia using our embassy reference monitors for calibration. Another project implemented by Duke University in South Asia uses a hybrid network that introduces satellite imagery to tie together sensor networks. The second element I'd like to emphasize about our programming is its focus on people. Of course, high quality data is necessary, but we need air quality practitioners to interpret that data and figure out how to improve air quality. That is why events like this one are crucial in bringing practitioners together to share and expand their knowledge. Again, I'd like to thank the organizers of today's event and for all of you for dedicating your time and energy to making the world a cleaner and healthier place to breathe and live. I wish you success in today's discussions. Back to you, Ever.
Thank you so much, Tom, for that wonderful opening remarks and to give an insight on the work of the US Embassy as well. So now I will introduce our second speaker, and she is Ms. Soraya Simon, and she is the Air Quality Coordinator of the United Nations Environment Program. She provides support to the strategic development of air quality work in UNEP, including to refine UNEP's offer on air pollution in the context of medium-term strategy, while improving coordination and internal communication and collaboration with other stakeholders, both internally and externally. I'll now give the floor to Soraya.
Thank you, Heather. Can you hear me okay?
Yes, we can hear you, Soraya.
Thank you so much. Ladies and gentlemen, colleagues, good morning, good afternoon rather, for those of you who are in the Asia-Pacific region. It gives me great pleasure to be with you today to discuss such an important issues related to air quality management. Air pollution is a critical state, as we just heard, and continues to be the world's single largest environmental health risk. 92% of the world's population live in areas where WHO air quality guidelines are not met, and I'm afraid that the situation is not better in the Asia-Pacific region. Without policy intervention, exposure to fine particulate matter, or PM 2.5, would increase by 50% by 2030. Everyone is affected, but the impacts fall heavily on the most vulnerable: children, women, elderly, and people living in poverty. With early studies suggesting that air pollution may be putting people further at risk during this pandemic, this gives us yet another reason to urgently improve air quality. The good news is that countries are taking actions to reduce air pollution. In a new UNEP publication launched on 7 September during the International Day of Clean Air for Blue Skies, we reviewed policy actions of member states to improve air quality, and this was based on the mandate given by the United Nations Environment Assembly 3/8 on preventing and reducing pollution to improve air quality globally. A key finding of this report is that overall progress in undertaking key actions that can significantly improve air quality. For example, in the Asia-Pacific region, there has been significant increase in access to clean cooking, drastically reducing exposures and attributable death in the region. More than 500 people have benefited from clean cooking and heating programs adopted in 28 countries since 2016, when UNEP undertook the first review of air quality policies and actions. There has also been progress in adopting conventional measures to reduce vehicle emissions, with 23 out of the 41 countries of the region having vehicle emission standards as of 2020. Also, 14 of the countries had light-duty vehicle emission standards at Euro 4 or equivalent, compared to only 8 countries in 2016. This action had positive impact on air quality. The State of Global Air 2020 report estimates that population wave PM 2.5 level in half of the country in the region reduced from 2015 to 2019. But the same report establishes that while progress can be observed in the sectors I mentioned above, significant gaps remain, especially when it comes to enabling policy framework to accompany the sectoral measures. And this, of course, is from the same report and another report that was launched by UNEP on the same day, or culminating with the International Day of Clean Air for Blue Skies. 1 in 3 countries in the world lack any legally mandated standards for outdoor air quality, based on the first ever assessment of air quality legislation published by UNEP last week. At least 31% of countries with powers to introduce standards have not used them. We also need the investment to match the problem. Unfortunately, based on a new report by the Clean Air Fund, less than 1% of the total official development aid is spent to air pollution projects, despite air quality related deaths in countries receiving aid rising by 153% in the past 30 years. Finally, while there has been promising developments in monitoring system, there are still significant data and capacity challenges. Many countries and cities continue to struggle to establish and maintain a sustainable air, to have continuous monitoring at multiple sites. And they don't have enough monitors to adequately characterize exposure for the size of the population. 60% of the countries, accounting for 1.3 billion people, or 18% of the global population, have no routine annual ground-based monitoring of PM 2.5 at all. Of course, while monitoring by itself doesn't reduce emission, the data and information generated from monitoring networks can serve to build the knowledge about the scope of the problem and can represent a great catalyst for action. For example, in China, the improved understanding on the scale and impact of air pollution prompted the government to declare a war against air pollution and set forward the Air Pollution Action Plan in 2013, which helped improve air quality levels. For example, Beijing observed 35% reduction in annual PM 2.5 levels within the 5-year period. There are also promising developments in health observation systems and emerging technologies which can support local efforts to better understand air quality status while complementing regulatory monitoring networks. Opportunities to further strengthen air quality monitoring efforts is what we hope to explore today at the second technical meeting of the Communities of Practice on Air Quality in Asia Pacific. We look forward to hearing your views, experiences, successes, and challenges on air quality monitoring and how we can support from UNEP and through our partners. Our collective effort on air quality monitoring is a valuable resource to ensure that actions and commitments to reduce air pollution are realized and that there is visible and measurable improvements in the air we breathe. Finally, I would like to take this opportunity to sincerely thank the United States Department of State for their generous support to help strengthen regional communities on air quality in the region, and our partner Clean Air Asia for efforts to deliver this event. I wish you fruitful discussion. Thank you very much. Back to you, Ever.
Thank you very much, Soraya, for that very inspiring context that we have achieved significant effort through the years, but we must continue to work together, continue to build each other so that we can really do actions towards air pollution. Thank you very much. And now I would like to call on Attorney Glinda Bathan-Baterina from Clean Air Asia to provide us more information, to give an introduction of the session. And she is actually the Deputy Executive Director of Clean Air Asia, and she practices law with 20 years of experience in policy and program development for clean air, sustainable transport, industrial emissions control, and climate change mitigation. She's one of the lawyers who aided in drafting the Philippine Clean Air Act, implementing rules and regulations, and spearheaded the Asia Clean Fuels and Vehicles program. And she also, of course, plays a key role in leading Clean Air Asia projects in the region. Ms. Glintz?
Thank you very much, Ever. Good morning, good afternoon, good evening to everyone. Many times this week, we have heard it emphasized that clean air is a basic human right and that people have the right to breathe clean air. Based on this premise, information on the quality of air that people breathe is essential for governments to protect our right to clean air, to assess the effectiveness of policies and measures, and important for us as individuals to avoid the health harms that exposure to toxic air pollutants may cause. Many countries and cities still struggle to establish and sustain air quality monitoring systems. But thankfully, advancements in micro-air sensors and remote sensing techniques, combined with conventional reference air quality monitors, provide opportunities to bridge gaps in air quality data and information. Clean Air Asia is honored to be partnered with the United Nations Environment Program, the Asia Pacific Clean Air Partnership, with support from the United States Department of State in setting up communities of practice on critical air quality management issues, and in organizing this technical session on the use of hybrid systems to strengthen the community of practice on air quality monitoring. In this meeting, we aim to discuss the challenges, but more importantly, the solution, adopting hybrid quality monitoring systems for air quality management. We will hear about recent developments in sensor technology and methods of evaluation for air quality monitoring. And we hope that through this meeting, we will help strengthen the community of practice on air quality monitoring. I am so pleased to see that we have more than 70 participants, and the number is growing by the minute. Several of you we have worked with, and from 13 Asian countries participating in this community of practice technical meeting. With your active participation, we hope to achieve the meeting objectives. Over to you, Ever. Thank you.
Thank you very much, Ms. Glinda, for explaining and introducing the session. And in particular, for the session focus, we want to, as mentioned by Ms. Glinda, we want to look into the status, developments, challenges, solutions, and lessons learned in the use of hybrid systems. This is so we can strengthen the community of practice on air quality monitoring. And specifically, the objectives that we have identified for the meeting are here, showing that we want to really identify and discuss the challenges, solutions, considerations to adopt hybrid air quality monitoring systems. We also want to share recent developments in sensor technology and methods of evaluation for a wider application in air quality monitoring, and also to provide technical and management advice to air quality practitioners so that it can help strengthen the community of practice, effectively contributing to the sustainability of air quality monitoring efforts. And as you may have received in the agenda, here is the flow of our discussion. So we are done with the introductions, and the next part would be on satellite measurement and air sensor technologies, maximizing potential and use. So this is a 45-minute presentation from our esteemed experts, which we will introduce in a while. After that, we will look into the community of practice on air quality monitoring in Asia through a World Cafe format. So we wanted to ensure that this is a two-way discussion with hearing from your insights, your learning, your questions. And this is later on, we will explain that we will be divided into breakout groups and we will have discussion topics. Afterwards, we will have a panel discussion. The title is Technology as Solution, From Data to Action. And of course, after that, we will wrap up the session with a summary and way forward. A very quick break, but what we would do instead is to show a few videos from the AppCap week. All right, so in this session, what we're going to talk about is satellite measurement and air sensor technologies, maximizing potential and use. The session will discuss an overview of the status and future of technologies available to monitor air quality, as well as insights on the capabilities and performance of monitoring technologies employed, and policy and technical recommendations to sustain these types of air quality monitoring systems. We actually have a very exciting panel. We have Dr. Pawan Gupta from NASA, Dr. Andrea Clements from USEPA, and Ms. Karine Leger from Airparif. To give you a bit more of a description of the work of Dr. Pawan Gupta, we will actually, unfortunately, because of the time differences in the US, they wouldn't be able to join us physically today with Dr. Pawan and Dr. Clements, but they have sent us a pre-recorded presentation, and we already asked them some questions that will most likely be asked during the session. And to give you an insight on the work of Dr. Pawan Gupta is a senior scientist working at the University Space Research Association, NASA Marshall Space Flight Center. The focus of his primary research expertise is aerosols, trace gases, fires, and climate remote sensing, which includes atmospheric composition retrieval algorithm development and validation and application of satellite data for air quality and fire monitoring, forecasting, and assessment. Dr. Gupta also leads NASA's Applied Remote Sensing Training Programs, or RSET, focused on health and air quality. So with this, we will now play Dr. Pawan Gupta's presentation.
Thanks for the invite. Today I will be talking about some exciting and new capabilities for monitoring and forecasting air quality in Asia. The slide shows three key components of air quality monitoring. Traditionally, air quality monitoring has been done using instruments on the ground. These monitors are usually very accurate, but the map near the top shows the location of ground monitors of PM2.5 around the globe, and you can see the large gaps in coverage, even in countries with a lot of monitors. Satellite data can help fill in these gaps in coverage and provide information where there is no information from the ground is available. Atmospheric models are needed to predict future air quality. Together, these three components can comprehensively observe and predict air quality. So what determines ambient pollution concentration? Air quality monitoring does not mean concentration measurement alone. It required a lot more measurements and analysis to understand the local and regional air quality. Along with emissions from individual sources, local and removal essentially controls the concentration of pollution near the surface. Similar measurements in the column of the atmosphere are also important, specifically when using satellite observations. There are many different types of regional and global network providing continuous measurements of surface and column loading of particles in the atmosphere. These measurements are highly relevant for both air quality and climate change applications and research. NASA's AeroNet networks serve as ground truth and provide fundamental measurement for validating satellite-retrieved aerosols data. OpenAQ is an open source air quality database collected from regulatory grade monitors around the world. Spartan is an emerging network providing optical and chemical measurement to support satellite data product development and validation, whereas the Purple Air is an exponentially growing network of low-cost sensors with open data policy. In addition to these global networks, many countries have their own networks with some open data and many not so open. Open data policy is key to make progress in understanding and controlling air pollution all around the globe. In one of our efforts, we are using individual citizen scientists to collect air quality data from their home, office, or community locations using outdoor Purple Air PM2.5 sensor. Through this NASA-funded project, we deployed about 400 sensors in 3 geographical regions, one in California in US, North Carolina, another region in US, and India. The scientific objective of this project is twofold. One is to evaluate the quality of data coming from the low-cost sensors, and then integrating that data with satellite observations to understand satellite measurements better around the globe. Initial results of this census data evaluation in two completely different environment conditions are shown here. The top panels shows data from India with pollution levels are very high, PM2.5 values ranging up to 600 microgram per cubic meter. The bottom panels are from North Carolina in US. Pollution levels are very low. PM2.5 values are less than 10 microgram per cubic meter most of the time. The left panel shows the purple air sensor performance without any corrections, where you can see the performance varies. Over India, it does shows pretty good performance. Over North Carolina, under very clean conditions, it does have its own variability. Whereas the right panel shows the improved performance after making calibration correction using machine learning algorithm over both India and North Carolina. So these exercises demonstrate that with careful data collection and calibration, data quality from these low-cost sensors can be improved and data may be useful for scientific data analysis. After looking ground, let's review what is available from the satellite observations. So there are three main types of satellite providing air quality measurement. The geosensors operates satellites in geostationary orbit, looking down and making high temporal resolution measurements of a given parts of the Earth. The LEO or low Earth orbiting satellites, or also called polar orbiting satellites, provide global coverage but only make once per day measurements under cloud-free conditions. Then there are one sensors located at L1 orbit called Discover or Apex sensor. It's make measurements over daylight portion of Earth every 90 minutes. The figure on the left shows the spatial and temporal scales at which current and future satellite observations are available. It's clear that we are close to time when we will have a global hourly measurements with 1 kilometer spatial resolution. As you can see, number of sensors listed already in orbit providing that temporal and spatial scales measurement useful for air quality monitoring. So what we can expect in near future in terms of aerosols data availability from space for surface air quality application. Here is an example where under a NASA measures project, we are running MODIS dark target aerosol retrieval algorithm consistently on 3 LEO sensors on the bottom called MODIS, on Terra, MODIS Aqua, and VIIRS on SUMI and PP, and 3 GEO on the top sensors, which is goes east, goes west, and Himawari, combining the data into a consistent gridded format in 30-minute intervals. So the middle panel shows a data fusion of all these 6 sensors. Global aerosol product like this and many others provide an excellent opportunity and challenge to develop new algorithm for operational global PM 2.5 datasets. In another similar attempt, we designed a simple machine learning algorithm to generate daily PM 2.5 maps while combining fires and aerosols data from the VIIRS sensors over India. We also used GEOS forecasted meteorological field and surface measurement from regulatory as well as low-cost sensors to train our model. In this example, a true color image from November 9 is shown and corresponding daily mean PM 2.5 is mapped for that day on the right panel. The resulting map does capture the spatial pattern as seen in RGB image. Due to the small nature of agriculture fires and relatively calm weather conditions during this time of the year, most smoke from these fires are expected to stay within the boundary layer and hence increasing PM 2.5 concentration near the surface. Last year, we organized a weekly community forum to provide near real-time analysis of fires and air quality using multiple satellite observation during India's post-monsoon agricultural burning season, which creates air pollution problem almost every year. The analysis and processed data are provided through a web portal. We are going to be providing similar analysis this year as the fire season starts. Here is another example where we use satellite observation successfully to estimate the impact of lockdown due to ongoing pandemic. In the spring 2020, India imposed a complete lockdown, which include shutdown of most of the emission sources. This was a natural experiment to understand how the shutting down the emission impact the local and regional pollution concentration. In this analysis, we used Moody's aerosols and ground data to estimate the reduction in pollution in year 2020 as compared to baseline concentration using data from 2017 to 2019. We found significant reduction across Indo-Gangetic Plain, as you can see on the map for 2020 versus baseline map on the left. Since then, hundreds of similar studies from around the world published and found similar results with varying magnitude of reduction depending on the strictness of lockdown and methods and data utilized in specific studies. More recently, we applied NASA satellite and model outputs to generate a 3-hourly PM 2.5 forecast for the Thailand and implemented into a web application with real-time validation capabilities. This particular application is currently adopted by Thai Pollution Control Department, and we perform this work in partnership with NASA Surveyor Program, which is a partnership between NASA and USAID with local partners in the region. There are more details on this tools available on the website, which is given on the slide. In a similar efforts, we are working through NASA's Health and Air Quality Applied Science team with US Department of State to provide air quality forecast on locations of US embassies all around the globe. This will also this is a relatively new project which we just started earlier this year and expected to complete in next few years. Once this project is completed, we will have capability of 3-day forecast on all locations of embassies all around the globe. And finally, I like to point to some upcoming air quality satellite missions which will change the way we monitor air quality from space. The first one is constellation of air quality sensors in geostationary orbit. There will be 3 very similar satellites in geostationary orbit providing hourly measurement of many trace gases and aerosols components relevant for air quality application. The GEMS by South Korea is already launched and providing the data over Asia. Tempo and Sentinel will make measurement over North America and Europe respectively and are scheduled to launch in next couple of years. In addition to this constellation of geostationary satellite, NASA is also launching a new missions called Maya towards the end of next year. And the focus of this new mission is to make high resolution PM 2.5 and speciation measurement over large urban centers around the world with very high spatial resolution. The data will be specifically used for health impact analysis with local and regional partners. And that is all I have. Again, thank you very much for the opportunity. Have a good day.
Of course, we're very thankful to Dr. Pawan for giving his time for this session. And indeed, you can see in his presentation how extensive data can be collected with the combination of both ground-based and satellite-based measurements. Before we discuss question and answer, before we do have questions and answers, I would like to continue giving the the context of the background of our next speaker. So our next speaker is Dr. Andrea Clements, and she is a physical scientist working on the characterization of ambient air quality. At the USEPA, she works in characterizing emerging technology for measuring air pollutants. Her current work involves evaluating affordable air sensors and providing guidance for their use by a range of groups, which include communities and individual users. So now let's hear from Dr. Andrea.
Hello, I'm Andrea Clements with EPA's Office of Research and Development. Today I've been asked to talk to you about the capabilities and performance of air sensor technology. After putting us on the same page, I would also like to take just a minute to talk about EPA's efforts to standardize testing protocols and performance metrics for the evaluation of air sensors, and highlight just one project where we were able to take air sensor data and combine it with several other data sources to provide the public with information about smoke during wildfire season. So to get started, generally when we talk about air sensors, what we're talking about are pieces of equipment that are smaller, lower in cost, more portable, and easier to use than the traditional federal reference or equivalent method instruments that we typically use for regulatory monitoring within the United States. Many of these devices return highly variable data quality, and we see that sensors perform better for some pollutants than for others. But in general, we find that the data quality is not as accurate as that returned from the much more expensive FRM or FEM regulatory data, and that sensor data often needs to be cleaned and corrected in order for these two data sources to become more comparable. In the United States, there's been a decision that air sensors are typically not appropriate for regulatory grade monitoring, but instead may be a valuable resource for non-regulatory, supplemental, and informational monitoring applications. And those can range from education to supplementing the air monitoring network. Typically, air sensors return data in real time at a high time resolution, so we can get immediate answers with a new measurement every 1 minute or so. Unlike regulatory instruments, sensors often lack status indicators, so we often don't know if they're performing correctly or not, and so we do have to keep a very close eye on the data. Experience shows that often particulate matter sensors have an average lifespan of about 3 to 5 years, and that gas sensors may have a lifespan of about 6 months to 2 years. But this is highly variable and really is still an unknown, because we have seen sensors fail right out of the box. Some hang on for a long time. We've seen sensitivity degrade, and we've seen sensors return random data after an unknown period of time. We also think that the performance of sensors may be variable depending on where they're operated and at what concentration range they're operated in. As I mentioned, we need to keep a close eye on the data. And some of the things that we've noticed about sensor data is that it can often include short-term spikes, spurious data, or the baseline can drift. And so sometimes we need to do some extensive data cleaning procedures in order to improve the quality of the data. And we often look at longer-term averages to have more confidence in the data as well. There are a number of different gas sensors on the market today, and they include ozone sensors. We've typically seen that these can be fairly accurate and reliable, especially if they can be co-located with a reference monitor for a while. We haven't had very good luck with nitrogen dioxide sensors. In fact, the performance is highly variable. And so when we buy one, we are not often aware if it's going to be a good one or if it's going to be a poor one, even if it comes from the same manufacturer. And we have seen that there are strong cross-sensitivities with other pollutants, including ozone. Carbon monoxide sensors are fairly accurate and reliable, but the concentration does need to be a little bit elevated. And we also see that SO2 sensors are more useful when concentrations are elevated as well. Again, the performance can be highly variable, and these sensors tend to be very sensitive to meteorology as well, so temperature and relative humidity fluctuations. There are a number of sensors on the market that claim to measure VOCs, and it's important to understand that typically we're not talking about a speciated measurement. So you can't get a concentration of benzene or a concentration of toluene, for instance, but you kind of get an estimation of a total VOC concentration. But again, you really can't subscribe that to a concentration of any particular VOC. We found some success in using these sensors to monitor leaks. Basically, do you know that there's a VOC source present or not? By far, particulate matter sensors are most popular and most abundant. It's important to understand that PM sensors tend to measure using an optical approach, which means they're only going to be able to see particles within a certain size range. In general, that's about 0.5 to 2.5 microns in diameter. And that there are a lot of assumptions that go into making a measurement of an observation of a particle and turning that into a concentration. And what's really important to understand is that if the type of particle you see changes, so might the performance of your sensor. And I will also add that generally PM 2.5 measurements are much more robust than, for instance, the PM 10 measurement, which really can't be relied on mainly because of this issue in seeing only a certain size of particles. Generally, PM 2.5 sensors tend to track the ups and downs of PM 2.5 concentrations in the atmosphere. However, the absolute concentration measured by a sensor may be inaccurate and may be biased high or low. We also see that there's wide variation in precision. In the images I show here, on the top panel, we actually have 3 sensors of the same make and model, which are measuring almost identically. This is a sensor with very tight precision. Whereas at the bottom, we have 6 sensors of a different make and model that do not measure very similarly. And this can have strong implications about how we can interpret and or correct that data. For instance, in the top, we might be able to apply one correction to all sensors, whereas in the bottom, each sensor might need its own correction. We also see that sensor packages with the same internal components may actually perform very differently in the field. Here we see that sometimes the orientation of the sensor within the box, the design of the housing, and or data correction approaches may be different between the 2 sensor pods and therefore yield very different data quality. In the United States, we often compare a sensor measurement to that of a regulatory grade instrument in order to correct that data. Oftentimes, concentrations in the United States are low enough that a linear correction often does most of the work. However, if we're talking about a large concentration range, the comparison may not stay linear over the entire range. And on the right-hand side is an example where we're looking at wildfire smoke over a very large range. And in this case, we could not use a linear correction. So it is important to understand what is the concentration range you may be experiencing in order to understand how the data may need to be corrected. And on the last bullet here, I mentioned that a large shift in aerosol properties can change the relationship between a sensor and a regulatory instrument. In this case, we went from a typical ambient particle to a seasonal dust source. And in this case, that shift in aerosol properties changed the relationship. Now, with that kind of background behind us, I would like to mention EPA's work in developing standardized testing protocols and metrics for the evaluation of air sensors. There are a number of organizations worldwide that try to evaluate the performance of sensors, both under ambient or outdoor field situations and also controlled laboratory conditions. However, it's really hard for someone who's considering purchasing a sensor to interpret some of these results, largely because the metrics or the methods are not all the same. So EPA has recently released 2 reports that outline our recommendations for performance testing protocols, metrics to describe the performance, and also target values, which we hope sensors can meet for measurement of ozone and fine particulate matter. The bottom line here is that our goal is to provide a consistent approach for testing sensors and a consistent approach for presenting the evaluation data to the community. Our hope is that people can look at these metrics and look at an apples-to-apples comparison between two different sensor types, and therefore be able to make a more informed decision about which sensor is most appropriate to meet their intended application. And we also hope that by setting some targets, we can encourage innovation in the marketplace and improve the performance of air sensors on the market today. And you can find those reports on our website. Lastly, I just want to highlight one example of integrating sensor data with other types of data to provide a more consistent picture of air quality during wildfires. One of the great promises of sensors is that we should be able to supplement our air monitoring networks to provide more measurements in more places where we need them most, which could include rural areas or mountainous areas, especially when impacted by smoke. When we first started this work, we actually looked at the purple air sensor, mainly because it was a large repository of crowdsourced PM2.5 sensor data. Generally, people were purchasing these and putting them at their homes to learn about local air quality conditions. We started by evaluating how well those sensors performed relative to the regulatory monitors that we have deployed across the United States. In the upper right-hand corner, we did echolocations during typical ambient conditions, spanning from 3 months to a year. We also evaluated how well that sensor performed in elevated concentrations as a result of smoke from prescribed or wildfires. And then in 2020, we had some very extreme wildfires in the California and Oregon area where we were able to see how the sensor compared to regulatory monitors at very high concentrations. The result of all this work helped us understand that there was a relationship between the sensors and the regulatory monitors, and that we could apply one extended US-wide correction to the data to make the sensor data more comparable to the regulatory grade air monitoring data. And in this figure here, we just showed that this correction performed better than all of the other corrections currently available on the purple air map. And we were able to replicate the actual concentration to within about a 20% error. And so this gave us great confidence in reporting the air quality index. So this work resulted in the integration of sensor data with regulatory monitoring data on the AirNow fire and smoke map. On this particular map, we can see regulatory monitoring data in circles, temporary monitors, which are typically put out to look for wildfire smoke, in triangles, and in the squares is a whole network of crowdsourced purple air data that has been added to this map after the data has been cleaned and corrected using the extended US-wide correction. Not only are these ground level measurements integrated into one picture where we see some consistent performance, but we also overlaid satellite smoke detection and also information about fires that were going on within the country too. And together, all of this data helps to provide more information at a more local scale for communities that are impacted by smoke. With that, I also just want to point you to the Air Sensors Toolbox, which is our portal for being able to share more information about air sensors, their performance, and all of our other resources that we have to help people use this technology most effectively. And although I won't be able to join you for the question and answer period today, I do invite you to reach out to me by email with any of your questions. Thank you so much for your time and attention today. All my best.
So we're very thankful to Dr. Andrea Clements for giving her time and expertise for this session. We have some questions in the chat box and we will address them later on. For now, I will proceed to introducing our third speaker. So we have, and she is, of course, we're very thankful that she is here with us today to give her presentation live. And we have Miss Karine Leger from Airparif, and she is an environmental engineer and the Directorate General at Airparif. For 20 years, she has been involved in projects related to air quality measurements and public information in a region in Paris where these topics are considered sensitive issues. She has been involved in cooperation with Airparif counterparts in large cities across the world which are facing the same challenges as well as in European and international projects. So we'll now give the floor to Ms. Karim.
Good morning. It's a great pleasure and a great honor for me to be here today. Good morning or good afternoon. I first would like to thank the organizer, the US Embassy, as well as the UN Environmental Program and Clean Air Asia for the great organization. What I would like to present today is how we use, what are the perspectives regarding hybrid monitoring for a monitoring agency like Airparif. We are the independent organization in charge of monitoring air pollution for Paris region. We are 40 years old, 40 years of expertise regarding air pollution monitoring. In our administration board, we have different stakeholders because we have the local authority, we have the states, we have also economical players and NGOs. And we make available all the information that are produced by our organization. We are in charge of monitoring, understanding and analyzing atmospheric phenomena, assessing and advising decision makers and citizens, including regarding new technologies, and supporting scientific, technical, and social innovation. Hybrid monitoring is somehow already a reality for us because the monitoring in Paris regions rely on different tools, reference network with station and diffusion tubes, emission inventories with real information on the traffic, real-time information on the traffic, and modeling tools that we use for forecasting, but that we use also for impact assessment with a 10-meter resolution in Paris for 5 pollutants, updated every hours. First, I would like to say that there is no perfect tool. It really depends on your needs. There are different needs regarding monitoring, compliance checking, mapping, forecasting, informing the citizens, scenario running, impact assessment. And all these tools are continuously developing as well as the level of pollutant, and there are also, let's say, new pollutant or emerging pollutants that need to be monitored as well. For us, the key issue is really the quality of the data. Our data are used by all the stakeholders, the authorities for mitigation plans, court cases that are getting more numerous, the general public and the media to be informed, to raise awareness, but also to protect themselves, to reduce their exposure, researchers, and as well as economical players to develop products and services. And this is in a context where air pollution, as you mentioned, Evelyn, is very sensitive. It's a relation with health, and this relation is enhanced by the COVID effect, environment, and the link with climate change, economical, with the labor cost, a question of city attractiveness. Air pollution is also a market for different kind of companies. It is a regulatory framework with legal disputes with the national government, but also with the European Commission. And it has an impact in the international relationship, as it has been mentioned by the US Embassy. Therefore, it's a very mediatized and political issue. And I would say as a regional authority monitoring and informing about air pollution, you better be sure about every microgram and number of persons exposed, because the penalty we will have to pay with the European Commission really depend on our data. As such, we have been testing and developing different kind of technology, and we are monitoring the new or developing technology to see how we can use them, both to improve the knowledge, but also, if possible, to reduce the cost of monitoring. We have worked a lot regarding on microsensors for more than 10 years, because it's really something which is developing and it is developing fast. And we ran a challenge. It's somehow the same kind of performance testing done by the USEPA, and the USEPA is involved in the next workshop, which will be released in the 13th of October. And with this challenge, we want to link the sensor with the use. The performance of the sensors might be quite different depending on the use, not only depending on the brand and the pollutants. We want to provide or highlight the most relevant technology depending on this use. We want to be to advise the possible users, including our administration board, the authorities, the companies, the NGOs, to have some sort of technological state of the art and to support innovation, because those microsensors are also developing over the time. It's a periodic evaluation campaign in a realistic condition in a lab, but also on site. And it's based on multiple parameters, but it's like for the USEPA, it's not a certification tool. And it's associating an international expertise with a strong evaluation panel, and the workshop that can be circulated on the 13th of October will also involve the USEPA. This challenge, as I mentioned, is testing different kind of sensors for the use outdoor, indoor, and also for citizen participation. Then at the end, we provide this kind of file regarding each sensor, the name, the performance for different parameters, not only the reliability, but also the cost, the relevance, the accuracy regarding different pollutants, and the ergonomics that can be important, for instance, for citizens' participation or indoor measurements. It's based on a very strong cooperation of organizations, strong expertise from the evaluation panel. It's public, private, research, local, national, and international organization. And at the bottom, you can see the large number of brands that have been evaluated for the session of 2021. Then regarding microsensors, we tested them for different purposes. Here is an example with the municipality of Paris and Bloomberg Philanthropies for air quality monitoring in Parisian schools. What we wanted to see is if microsensors could provide an added value regarding the existing information we have for the air quality around schools. For this purpose, we had 150 microsensors associated with diffusion tubes, because we need to understand when they work and when they don't work, but if we can use them or not. The feedbacks is that the PM sensors can be used for background conditions, but the algorithm really needs to be improved based on the reference monitoring network. And it didn't really bring any additional information compared to what we already had. For NO2, we couldn't use the sensors at all. The better information were provided by diffusion tubes. And at the end, we really had a question regarding, and I think it's a key question for any organization. It's really the look at the cost and benefit of using a network of microsensors. Then we tested them also for impact assessment on a very, very sensitive issue, which was the lockdown of the traffic around the Seine River. We had our network, models, monitoring campaign, reference stations. And in addition to that, we had 80 microsensors for NO2 and PM, and still diffusion tubes. And we didn't recommend to use the microsensors for such an issue, which was very sensitive, and also with court cases at the end, because it was really not reliable enough. We also did several experiments, including with UNEP regarding raising awareness and citizens' participation with the municipality of Paris, with the states. And it's really, really useful to use microsensors because it's a real driver for understanding air quality. And sometimes the perception of the person can be quite different from the reality, and it helps to make it more understandable. But you need training and pedagogical support to reach this goal. And but it really helps to develop skills and knowledge and change behavior, because at the end it's also what we want to improve air quality. The work we have going on is to use a large monitoring network of 600 microsensors to see if they can be used to improve the model, and this is still going on. Then regarding satellites, they are already used to improve our model or as input data for meteorological data, forecast systems, land cover, urbanized area, plant cover, soil humidity, topography. The data from the satellites are already used and working and implemented in our models. We can use them also to provide qualitative information about the boundary condition for large scale, providing information for large scale pictures on air pollution transport. Long-term trends, specific sources like large-scale fires and ships. There are research we are involved in regarding improvement of emission inventories with reverse molding, but it's still researches. And the current limit we have that maybe that can be improved with the next generation of satellites is the question of resolution. Several kilometers, it's too large for most cities. The update, depending on the number of orbits, the accuracy, but also the cloud-free condition and the cost of the data at the end. Some example we did based on the ground measurement, high resolution models and emission inventory. We did also an impact assessment of the lockdown that was quite precise regarding the needs you have to know the sources and the need for interpretation that has been mentioned at the beginning by the US Embassy. And we could show that the main improvements in Paris was related with traffic restriction, but there was less impact on PM because of the multiple sources, but also because we still had sources from wood burning for heating purposes, and the agriculture was not concerned at all by the restriction. However, the satellites, they provide us the larger pictures, and they are quite good to raise awareness regarding what's happening in the surrounding areas and at the national scale. So to finish with maybe some lesson learned, hybrid monitoring is already a reality. This is all the bricks we use in our modeling tools to at the end provide information and impact assessment for the authorities. In red, you have what is already in place. For instance, weather data are already included from satellites, are already included in our models, which is partially used. It's boundary conditions coming from satellites. Topography is already in place. What is still at the research level, it's for emission inventory, how satellites could help to improve the emission inventory for the stations. Could satellites information or macro sensors supplement the information provided by the station? But it's also all the way around, because it has been shown by US EPA, but also from the intervention from NASA, you also need really reliable data to improve the algorithm and to calibrate both the microsensors and the satellite. So it's really a two-way work between these different kind of technologies. This is lesson learned from Paris region with a specific condition, weather condition and air pollution composition and level that have an impact on the microsensors and their performance. And a given monitoring network, which is quite developed and an expertise developed since 1979. It's really based also on partnerships. We have been able to make all these experiments and testing based on the work with authorities, a regional council, municipality of Paris, also international organizations like Bloomberg Philanthropy of the AFD. It's a public-private research partnership depending on the project, and it's mostly on microsensors. It's starting on its developing on satellites. As I mentioned, the partnership and the expertise is very important regarding this issue. It's interesting, I would say, almost everybody for different kind of reasons. Our counterparts in different regions, like in Beijing or Hanoi or Tehran, we have a cooperation agreement, but also London, Berlin, Milan. AFD is deeply involved with us in Hanoi, and Bloomberg Philanthropies is also deeply involved with the municipality of Paris regarding this new technology, including the US Embassy also in Paris and the French Embassy also in Bangkok and different places in Asia. Before using this technology, I think the first thing is really to ask yourself what for. There is, as I mentioned there is no perfect device. It's really dependent on your need, but also depends on your expertise and on the financial conditions. but do not display the result in real time, especially for microsensors, because post-treatment are absolutely needed before any use and communication, especially if air pollution is a sensitive issue in your region. There is an imperative need of existing reference measurements, station, diffusion tubes, whatever you want, but you really need to calibrate and to be able to check when these technologies are working or not, or also to improve also the algorithm. And pre and post-treatment tests are also needed because even if when you have a quite good device that have been quite good, well evaluated, the performance might be different between the test on the lab and when you want to have a large-scale monitoring, because the industrialization phase done by the the companies might be quite different, and the performance of the sensors might be also quite different. You need to calibrate the device before using them, and you need to check the deviation over time and improve the algorithm. Cost assessment must also be taken into account for environmental reasons. The lifetime of the sensors is not very long, but also the cost of the sensors, the cost of getting the data, the cost of interpretation and data analysis must not be underestimated. That's why for us, microsensors is neither low cost or no tech. No, it's not low cost and it's not low tech. It really requires multiple skills and expertise to make it work properly. For some uses, further development are needed, but the technology is really improving and we can see it depending on the different phases of the challenges. This is just a summary of what we feel regarding the use of microsensors and satellites plus a reference network. It really needs to be used to be improved for compliance checking and impact assessment. But there are already a lot of use that can be implemented, and especially for microsensors, awareness raising, citizens participation, it works very well. For indoor monitoring, it's also very promising. We use them, for instance, for CO2 monitoring in classrooms to know when you have to open the windows for better ventilation in the classroom, also related with the COVID situation. I would say as a monitoring agency, we are right in the middle between international comparison and citizens information, between top-down and bottom-up information regarding air pollution, and we are really interested in further sharing expertise, and especially in other contexts and with different weather and air pollution conditions. And I really thank you for your attention.
Thank you very much, Karine, for that elaborate description of the extent of work of Airparif on hybrid air quality monitoring systems. I think we have some questions in the chat box, and please do feel free. You can, in the meantime, you can reply to them through the chat while we proceed to the next part of the session. Thank you very much, Karine. So now we will proceed to the next part of our technical meeting, and this is the session which is entitled Looking into the Community of Practice on Air Quality Monitoring in Asia. This is a World Cafe format, and as what we have explained in the meeting reminders, the goal here is to have an open discussion within small breakout groups. What we want to discuss would be, what are the enabling environments? What do we need to consider? What are our needs in order for us to uptake hybrid air quality systems, or in general, air quality monitoring systems? We are also looking into strengthening air quality management systems by discussing challenges and solutions, and also talking about existing and potential collaborations. Here in this session, we are actually joined again by a very exciting panel. First, we have Mr. Timothy Dai from TD Environmental Services. He is an air quality sensor expert, entrepreneur, meteorologist, and the principal at TD Environmental Services. He is known for leading projects related to air sensors and the Internet of Things, or IoT, technologies used for environmental applications. He is also an expert when it comes to environmental field monitoring, data management, and public communication, and has experience for over 25 years. We will also be joined by Dr. Jihana. She's from the Institute Technology Bandung in Indonesia, and she is an associate professor with extensive work on air quality monitoring and management. Her recent works include the urban hybrid models for air pollution exposure assessment, or UDARA, which aims to establish exposure estimate models of nitrogen dioxide, ozone, and PM2.5, providing information on air quality and actions that must be taken to reduce health risks from air pollution. We are also joined by Dr. Meiwa Zhu from the Asia Center for Air Pollution Research in Japan. She's a senior researcher at the Planning and Training Department and Atmospheric Research Department at the Asia Center for Air Pollution Research, and she plays an important role in achieving the goal of ACAP in improving air quality and solving air pollution problems through research, collaborations, capacity building trainings, and monitoring of acid deposition and air pollution in East Asia. The esteemed experts will be joined by Cleaner Asia colleagues, Dang Espita Casanova, David Ekal, and myself. And as we have described in the email reminders, you will be automatically put in breakout rooms. And so this is the grouping, and don't worry about it because we will automatically put you in the assigned meeting room. Once you get access to the link which your note taker will provide in the meeting room, you will see this icon of a sticky note, and you can just click on that. Once you click on that sticky icon note, you can enter your response for the question presented in your room. So don't forget to write your name, affiliation, and country as well. Once you're done, you can just click on save, and it will show up in your virtual board. So with this, we're now requesting our IT to please put the participants in the meeting room.